So we have, as part of our ongoing dialogue series on Fridays, trying to get you some interesting things, cross currents in practice. Today we're going to look a little bit at the side of technology and the architectural technology sequence. We have three panel speakers here today. I'll introduce them briefly and then they'll say a couple of words about their work. After that, we're going to have some dialogue and open discussion, so I hope you have some questions and we can have some back and forth. First is Ben Gilmartin from Diller, Scofidio, Renfro. Ben's a partner there, has done some of their seminal projects, has been with the firm for a number of years. I've worked with him from Highline to, and he'll show a number of other projects that they do, including the culture shed down in Hudson Yards. Thorsten Helbig of Knippers Helbig, founder of a phenomenal engineering practice. They do very specialized advanced structural engineering and facades, and I'll show you all about that. And John Cerone from SHOP, probably know SHOP, architect, came out of Columbia and really have harnessed, I think, a new wave of technologies across our industry. The title of this is about interface, simply because for those who've been through classes with me, this area of interface is an area of very rapidly changing technology today. Whether it's on a roof, a facade, other elements where we have all these cross-pollinating demands, light, air, energy, material, water, things of that nature, all interfacing and converging. And what I'd like to talk about today is this idea of negotiating this convergence. But we'll get to that. I just wanted to set up this idea of convergence and what I see a little bit in the industry as this pattern. Probably recognize this, but just to suggest that roofs and envelopes and facades do much more than simply a building and look at them. They actually negotiate from exterior to interior. And they're very technical today. Something around the order of 70 to 80% of the energy consumption of a building can be controlled by selective use and specification of that facade system. But you have to modulate light and air and other things at that interface zone. So it's complex. And the industry in certain respects has bifurcated. It's gotten more specialized. There are now facade engineers who used to be architects. There are lighting specialists who used to be architects. There are all kinds of specialists, but at the same time, I would argue that we are converging because these demands of what we're designing for are converging. The demands are something that are more sophisticated than they've ever been before. What we are demanding from what we design is more sophisticated than ever before. A roof is not just a roof. It has to mimic a tree. It has to mimic a natural experience. It's not okay just to come under a mall and just sort of have sunshine coming through. We have to be in a very specific experience. So let me step back a little bit to some historical precedent because I want to get you into this mindset. When I first started, everything was about lightweight systems. This was not that long ago, but lightweight systems, this is in the 60s, and very fine and material, just engineering the one kind of structure to get to a lightweight system. Concrete shells as well, very, very thin, but they were really driven by a singular notional quality of material efficiency. Really, in a post-war sense, because there was so little material left post-war, post-World War II. Much of the development came at that time. In 1978, you started to see these shapes form. Technologies like, this is one of the first true grid shells made out of wood in Germany, the Mannheim guard shell. And it's a really fascinating project. You also saw these amazing cable structures and lightweight systems sort of emerging at that time in the 70s. And you saw these other projects that really took super, super thin elements to their extreme. Air-supported stadiums were the lightest way of spanning from A to B. And an awful, horrible experience inside. Nobody wants to go in and see a football game, or anything else for that matter, inside of an air-supported stadium. It's horrible. So we learned, it doesn't matter how efficient it is, it's still really horrible to be inside, so we don't build them anymore. Or we build them selectively, shall we say. And at some point we figured out how to span these huge distances with minimum material, but it wasn't enough. We then started thinking about shells, getting back to this sort of compressive shell-like system. And this is an early project I worked on at my firm, BurroHappold. When we were talking with the speakers before, the idea that you really, about the surface and the system, all of a sudden we have these surfaces that you could be transparent. It was amazing. Like before, really the surfaces had to be opaque up until this point. This is mid-90s technology. So all of a sudden you get this idea that, well, I can't, the concrete shell, now I can have a transparent concrete shell, which is really cool. And I can do it in all kinds of different geometries because I can figure out how a computer can run a machine, and you can cut all kinds of different nodes. But there was something missing even from that. From that technology, this is a project I did, I was involved in about 10 years later. And the reason that I compare these two projects is that we started to think about how that interface, that system, not just spanned, not just used its material, but how it actually, how light and acoustics and air flowed inside of this space from that interface condition. When this is down in Washington, D.C., and many people go to these two projects, and when they tell me their experiences, they're almost always saying that this is a great space inside. And it's not because the roof is cool, or I think it's not cool. It's because there's all these other things going on in the design of that interface. That's the sophistication that's happening today. ETFE is another material that's popped up. It's extremely lightweight. It's a project in California, sorry about the quality of the image, but you see these really lightweight pieces inside. But what's driving some of this is not necessarily the lightweight nature, but the environmental conditioning of what's going on in here. You can make something super transparent, but if it's hot as hell inside, nobody wants to be in it. And final thing to show, this is a project at the Louvre in Abu Dhabi, Jean Nouvel's roof for this museum. The concept being a whole series of pavilions over water and a roof that really just provides shade. A roof that actually stands above the ocean and actually doesn't have any glass to it. All it does is provide shade. It doesn't even provide waterproofing. And that shade provides a sort of an environmental filter to allow people to circulate within these galleries. And sort of end with this image, because this is one of the images that Jean Nouvel started with in this project. And it's a really haunting image to me, because it's incredibly authentic, particularly for those, if you've studied Islamic architecture or tried to get to the end result of something authentic in the Middle East, which is not easy, okay? But this idea that this is not even projected as a roof in this rendering. It's something else. It's almost like a canopy. It's almost like an interface we don't even know about, but it's controlling these rays of light. It's controlling how that person perceives the space. Sorry about that. That was a stadium that doesn't belong here. I started thinking about this idea of interface and all of these different words that we use for roofs or facades. Lightweight, efficient, sustainable, and iconic. And I started scratching them all off because it doesn't matter anymore, because it's really about something that is now converged and much more sophisticated. And as architects, you're going to be right in this space very quickly, if you're not already there in your studios. Deciding which of these words applies, if not all of them, to the things that you're doing. So, with that, as a setup, I would like to introduce Ben Gilmartin to talk a little bit about his work, and hopefully we can go through each of the speakers and then have some dialogue afterwards. Let me see, podium PC. Okay. Thank you. Okay. This is on me,
Okay.
so I think you're...
So I'm Ben Gilmartin. I'm from Diller, Scofidio, and Renfro, which is an architectural studio, and many other things as well. And I'll talk about several projects today to chart a trajectory through maybe a way of working that's experimental. It touches on the idea of skin and envelope in each case, and basically the invention is around the idea of the skin and the envelope, with the notion that all of our experimental works are highly collaborative with both our consultants, who are experts, for example, Thorsten here and Craig, but also with people in industry who are experts in manufacturing and installing things at the height of their field. So, typically the other piece of it is that we're using highly advanced digital tools now that weren't really available in the same way 10 years ago that allow us to talk to contractors in a new way. Well, first thing is, you know the Blur building, this is really no skin, but it's an envelope that's created purely out of atmosphere. There's no enclosure whatsoever. The studio is very known for this, and the only way the project was able to be realized with 35,000 fog nozzles, 13 control zones, built up from scratch, algorithmic software that reacts to environmental barometric pressure and wind, was through a high degree of collaboration, both with people with those expertises, but also with experts in the world who understood fog, like Me Industries, who built the fog pavilion in the 70s. Dutry, Biogenesis, and others. Alice Tully Hall, I'm running through projects very quickly. It's a project that I spent a number of years of my life on. It's not an exterior envelope, it's an interior envelope, but it's very high performing acoustically, and it has a special invention, which is, if you went from the Blur building to this is about the blush, which is that the skin itself has light behind the surface, and can actually emit light through its surface. It has complex curvature shapes and a really tight skin that all had to be prefabricated and pre-fitted before it came into the space. We began working with millworkers out of Japan in the early stages of our own exploration, research, and development. We collaborated with resin producers in the Midwest, Reform and SHOP out of Utah, that was very expert in woodworking, and went through a process of development that got us to a full-scale mock-up. We did a digital pre-build in COURTYARD. That was the first time that we did that, and we did it in collaboration at that time with Gary Technologies. Now we do it all in-house, but we built the entire space and everything that had to coordinate around it so that the skin could be fit. We knew every part, and we knew that everything fit correctly. It allowed a kind of parallel effort of fabrication off-site in the shop, fitting everything together, structure, skin, lighting, and all the performance elements that could be brought in trucks and installed, and help the contractor to coordinate the trade work on the site and get it to work correctly. And so that's a little bit overblown, but you kind of understand the light actually emitting from the surface on a veneer laminated on a resin core. Another project that was highly experimental, didn't go to full realization, was an inflated structure at the Hirshhorn Museum on the National Mall, SMITHSONIAN by Unshaft, and our proposal was to fill the courtyard with an inflatable structure that produced a space for our temporary events twice a year. That was the intended look of the thing. We collaborated with another excellent engineering outfit out of Germany, Form TL, who does tensile structures. They're really superb to develop the idea of this sort of PVC laminate or PVC coated polymer fabric structure that was about 3 millimeters thick. It's about 26 pounds per square foot. Pressure to inflate the structure is asymmetrical, so doing very careful analysis of the distribution of stresses through the skin modeling that very carefully as part of the work, and then ultimately we went into a design-build relationship with Nusli in Switzerland, who's an expert in tensile fabric structures. It almost got built, but it didn't get built because of the crashing economy, so it's a project that's sort of perpetually on hold. That was the feeling of the interior. I'm jumping through a series of projects and very quickly charting a trajectory, but the Broad in LA, which just opened, is a different kind of skin structure, but it is actually fundamentally a very thin-skinned glass building that has a very complex outer shell that filters daylight and forms the outer expression of the building. And so the party of the building is that Eli Broad's art is stored in the vault below, and that above it creates a column-free 200 by 200 foot area that basically is the space of exhibition, and that's enveloped with the veil, which is a both structural and daylight diffusing surface on all sides that's column-free for basically an acre of area over the top of the gallery. And this is just to show that this is the fragment of the wall going up to the ceiling, but the glass line actually passes between the wall and the ceiling very seamlessly with these 25 by 8 foot dead-loaded pieces of glass with no monuments that form the museum envelope on the inside, so there's a very seamless expression to the shell on the outside that brings daylight in. We built a COURTYARD model that identified all the different shell components on the facade and at the roof, both for bringing daylight in from the top and from the sides, and worked with Zila in Germany for a very highly coordinated steel frame structure clad in glass fiber reinforced concrete panels that produce the veil expression. And those elements ultimately, through that collaborative process, were produced off CNC fabricated molds, and then pre-engineered with their frames off-site, brought in. And I'm skipping through the story very quickly, but held on the steel frame at the exterior of the building, to kind of fine glass line and the kind of overhead glazing that makes a very large volume of kind of free universal light space at the top of the museum. So mainly today I want to focus on the shed, which we formerly called the Culture Shed. Now it's just called the Shed. It's a project that's being constructed at Hudson Yards on the west side of Manhattan, along with many other things that are being built there at the same time. It's directly adjacent to the High Line. So there you see it kind of looking from the southwest, from the Hudson. The area around is significantly more built up already. There's the KPF tower would be here, and there's a kind of retail component that's being built there. Right now, our structure is up actually to the roof at this point. That's the location. That's the initial image of the building. It's a Kunsthalle of about 200,000 square feet. Again, right on the High Line on the southern edge, and it's the Kunsthalle idea is that the square footage is basically available to. There's not a resident collection there. Basically, it's all kinds of art being brought in, performance, events of all kinds, concerts. And the notion of the shed is that there's the fixed building piece, which is about 120,000 square feet of column-free space in the dark orange box there in 3 floor levels. And then the shed structure itself nests over the top of it and can extend in order to produce another 15 to 20,000 square feet of additional space, a very large volume. And when it doesn't need that space, it retracts it and gives back the space to the public realm. So it uses entry crane technology and repurposes it for the use of the building. Basically, there's an image of it retracted and extended. You see the kind of cross-section, the 3 primary floors sandwiched with lobbies and event space above and below. I'll go through this pretty quickly, but this is just the planning. Typically, they're wide open floor plates, so when the shed's deployed at the ground floor, there's a gallery space, and it can extend into the area of the shed. And so you see the large volume of space. You see the kind of different sorts of activities that can go on here. Within the shed structure, everything is embedded, everything converges. So it's the structure that supports itself. It's the thing that works when the thing is moving kinetically. It has ETFE pillow enclosures that are very lightweight. They bring daylight in. And it has all the mechanical distribution down the sides. So it has all of its systems encapsulated in the structure of the shed. and it has basically daylight or it can be blacked out. It can be a flat floor or raked floor for performance. So you see different kinds of events that can happen in the space. The upper gallery can be an art gallery. This one's out of order, but it could also be a theater in various configurations. And the top is basically a dining event level. We modeled the whole thing digitally, so the Revit model has all of the building systems fully coordinated. The shed itself was modeled in COURTYARD to allow us to again that dialogue with fabricators, Schwitter in Italy. So this is primarily the COURTYARD model component, completely pre-built with all of its systems in the digital environment. So we were sure that everything's coordinated and working. Some quick shots of components that were fabricated and pre-fitted in Italy by Schwitter, and they again helped to develop the structural fabrication approach. So the bolted structure that comes in very large elements shipped to the site. Vector Flow Tech to develop the very large ETFE pillows that form the envelope to the leather. This is a little out of order too, but this is the scale of one of the sides of the shed. The drivers, these kind of fabricated electric motors that sit on the roof and push and pull the thing in and out with very low power, actually. And they can deploy in about 4 minutes. The bogies, which are those gantry crane type wheels that allow it to roll on tracks, and they're massive. And there's the kind of closer to the current state of the project. And I wanted to quickly show a little video just because it's fun, and then I'll give over the con. So this is just a little demonstration of the shed, both how it works programmatically and say technically. Sits on top of a deck that's spanning over the Hudson Yards. And it's got a steel frame for its fixed building. And then you see the shed kind of come into being around that. Structure, and it'll actually use the base structure to be built for staging on site. It has all the HVAC that it needs and electrical and everything else in the roof of the shed. It gets the service from below, underneath the highway. So there's the cross section of the building. You get to see that there are actually guillotine doors that can open and close so it can be open to the weather. And it allows another larger aperture for loading art or performance equipment in. The roof is also a very robust mechanism for rigging for space, not just for bringing things in and taking them out, but also for theater rigging and event rigging. And so you can see with the multi-level space in a fixed building, you can have all kinds of events at different scales, large art installations, performance, and out in the shed space, perhaps very, very large art installations. This is probably like the first order being put inside. Blackout, as I mentioned, so for example, for a dance performance, make a cool black box theater space. Second level can open up to provide the race to stage a theater and a concert. And the shed itself, when it gives back the closet, can also sort of act as a proscenium on the stage to the outdoor space, which is kind of a nice feature as well. You can rig right off of the overhang. Highly automatic. The video is also useful in showing from a conceptual point of view, how the roof functions, both for the building systems, but it's also a full catwalk system with chain hoists and rigging for all kinds of uses. Anything you can imagine is staged here.
Okay, thank you.
Do you have HDMI or?
Yeah. Very nice project, and as you probably hear, I'm from Germany. So I'm a bit jealous because actually the architecture in Germany at the moment is more boxes, and like I discussed with the guys. I was back in Germany last week and had a lot of discussions about that. The interesting things happen here in the US at the moment. I think US, let's say, architectural scene, they don't happen that much in Europe, but not at all in Germany. So that's. But on the other hand, so like when you talk about this kind of project, you have an Italian accent or German accent with all the contractors. So this is interesting. So in a way, there's kind of this balance, and I think we talk about it later. So I'm a German, as you probably hear, as said, and that's why I have to talk about. And I'm from Stuttgart. And Stuttgart is the city of cars, and I start every lecture I do with the car. And what I want to tell, this is. Daimler, Daimler invented the cars more or less 120 years ago, and this workshop is the workshop where he did it, and it's 5 minutes walk from my home in Stuttgart. So what they did, obviously, they invented these engines and how you do it, and Henry Ford then made it to a mass product. So that means he made it affordable to everybody. That's a lot of what you have to do. You have to create standards and repetition. And what I want to talk about is how this, let's say, fabrication technology drives our design methodology. I think now, if you look back, you have this quote from Henry Ford. So obviously, the variation was quite limited. Yeah, you could have any color, so long as it's black. So, but now in the car industry, you could actually, there's still a kind of standard, but the variety is much higher. And I think, in a way, I want to say, in the building industry, we still work like Henry Ford did. Right? We work with very limited numbers of standards. So, looking back, why is the car industry so far ahead? They use the technology you have and understood how to use it also to design the cars and to come up with a different product. I think it's an interesting approach. Maybe it's a bit difficult to compare. It's a mass product still, but it's a customized mass product using the technology you have to fabricate. Obviously, fabrication technology informs design methodology. So, looking back, and that's the project. I just use the project to explain what I want to talk about, our project. So, but maybe, just to show, we work in different settings. Let's say we work in a normal, traditional way with architects on the client side, like we did do now for Renfro Piano in Los Angeles, is the Academy of Motion Pictures, or Shenzhen, Fuchs's Airport, I will talk about this, or Columbus, Ohio, it's not an envelope for sure not, and the Cambridge Collier Memorial, but it's a more traditional way that we work with architects, but we also work with contractors directly, so they hire us to support them when they want to, when they are in contact or come in contact with a client, and the design team, like in Washington, I think Greg, your team worked on the client side, and we work then on the contractor side for the Institute of Peace. So we are on both ends from time to time. We are on both sides of the table, I would say. I will talk about this, how fabrication technology changes the design methodology. So when I started, and that's the time you talked about, structures and lightweight structures and Stuttgart and Frei Otto, lightweight is something that's embedded in our DNA. So and when you did a grid shell in the 1990s, you had to work on the base of repetition. So you have repeated elements because it was still, the fabrication technology was still based on kind of mass production methodology. And the first time I realized that the time might be over was when we worked for Frank Gehry's roof in Berlin. I was a young engineer. So we still work on the left-hand side, we still try to find geometries, and we'll see the project later. We still try to find geometries which would work based on repetition, but Gehry insisted to have a geometry which is not based on any repetition. So we we learned a lot. So that's the roof finally in Berlin, and maybe you know this. I talk about this grid shell roof. So what we've learned that at this time, I think it was around 2000, the first contractors had access to milling technology and let's say computer or digital fabrication based on digital tools. And also, it was not the engineer, but it was the architect. And you know that Gehry did this, CATIA, and he brought the technology to the design back. So they understood much earlier than we did as engineers, which is a shame, that you could use these digital tools to be more free and to create new designs. So in a way, that was the first time I've seen that in 1996 or something. And I still remember when I first saw the Rhino coming. So that's the result. Still looks like the old-fashioned construction, but it's based on a new fabrication and design methodology. What we then did in our own office, we started in 2001. We tried to further work with contractors actually to understand how grid shells could be designed, let's say, in another way based on this fabrication technology. And you see what we did around 2005, 2006. We developed a method with a contractor where you have the nodes and the bar and the interface. We work on this interface. It's highly precise, like a machine, and you just bolt it together and then on site. You don't like British Museum is still right inside. So I think in London, also London Westfield, we made full use of this technology, I think. And based on this, you see that's very easy to install because for grid shells, the real difficult thing also is not only fabrication, but it's then installation. It's very sensitive to geometrical implications. So you see that. So for me, that was actually the Berlin project with Gehry was like typically technology is a kind of, or development of technology is an evolutionary process. But you have seen the step. Right? We figured that. So now that's 2 years ago for a project in Bratislava. Now this is fully, let's say, adapted in the industry, and I think a lot of colleagues work with this kind of technology. So this is now it's from yesterday already, yeah? And you have to do the next step then in terms of applying technology. Some projects we worked on. So this is the way, this is one direction to work with contractors and to know what is feasible. Sometimes you get, as said, as in Berlin, you learn more from the industry that you can do other designs informed by the fabrication technology. Also, the integration of all disciplines, that's what we are really interested in, and I think there's a lot of potential. This is a museum. We work now with Stephen Hall in Houston, and you talked about building skins getting more active or performative. So what I think here you see is that the skin, obviously Stephen Hall likes to have the skin also, there's an expression, architectural expression for sure, but also the skin is being activated, so it works. And Transfer they call it cold jacket. I don't know whether this is the right phrase for that. We Germans try to create English phrases, which is difficult. But you see what it does. It's kind of transforming the wavelengths and the energy from the outside to the interior. So it obviously these glass or this semicircular glass facade kind of transforms the wavelengths, the UV wavelengths into heat. And this heat can be convected like in a chimney. So interesting for us, it's structural facade engineers to work on how that could be done, and we work with a contractors now, this is 6 meters, what is this, 18 feet, like long pieces out of laminated glass, semicircular glass components. That's interesting, and it's just possible because you work directly with these contractors. You try to figure out, and you for sure push the boundaries of how these things could be done. Also, maybe for Harvard with Stefan Benisch, what I've learned there. Also, we don't just talk about technology, but also we talk about new materials or the way we could understand materials. We work here, especially on the screen, on this, let's say, shading component, which is acting as a filter between outside and inside. And as you can imagine, the way it's informed by the sun, for sure. So, but we also we discussed it could be informed by the interior use. So to program the facade could be also like it might be a difference whether you're in an entrance lobby or in a lab somewhere on a library. So I think that's also an interesting thing. So that facades could be more as a transmitter, or let's say, as you say, could be more than just protecting against sun and wind and water. So, and what we found for these components, the performance is very clear what it has to do. So we thought about more what material it could be. So, and this is what my partner Jan is doing at the university. They do kind of material research. This is a biodegradable polymer. It's very interesting. So you can fully recycle it. It's based on organic material, and you could work with that actually. And we also this was a pavilion they did I think 2 years ago in Stuttgart, and we tried to apply this. It's a very interesting material, and we actually brought it up to a level where we got a bid for this. It's actually comparable, but you need a client who's willing to take a certain risk. What happens in 25 years, and we couldn't prove what happens in 25 years. We did some testing. I think it's one of the materials which will be in the future very interesting to work with. We now also on the way and developing ideas of having this screen like what we could do with it. We now work on a hydroform. It was interesting. This material now is a stainless steel. It's 1 mil thick, and once it's pressed into the mold, it's just 0.5 mil thick. So it's a very thin material, very efficient use. It's lightweight, as a kind of lightweight structure. And then you have to work with the form again. How to make material stable, which is so thin, like paper thin. Right? I think that's interesting, and at the moment, we are really curious to figure out what we do with it. So that's set, it will be built. We don't know exactly how it looks like now. Okay, so you see what they do. That's actually also like in a kind of interplay between the architect, structural and facade engineers we are, and engineers from the fabrication side. They developed this tool, these components with us. So I want to talk about how design methodology and using the tools we developed so far, BIM, Revit, and Rhino, with all these plug-in tools you could have, how this could change the design or the understanding of design. I want to use this project to explain it, or to at least to come up with our idea of how we see that. This was a competition in 2007, 2008. We won the competition in Shenzhen, China. And then we had 5 years time to develop and build the project until operation. So it's obviously a very large project. It's 1.3 kilometers long. It's a lot of members, and you can imagine such a shape you cannot develop based on a repetition of components. You have to rely on a digital tool to design it and then to fabricate it. So just to impress you how big it is. And Fuchs's idea was, especially for the skin, that over the length of this 1 kilometer concourse, you have different lighting scenarios. It's close to Hong Kong, and Hong Kong is a kind of repetition. Foster's Airport is a kind of repetition of components, and Fuchs's wanted to make it actually like another experience. So we have this idea of having these let's say openings in a way closed and open, static, but over the length of the airport or concourse as a kind of to create different lighting scenarios, like in the forest. Like you had this picture from the forest where, whether it's more closed or more open. So we did our own model here to understand this. And then we worked actually on this pattern, on this honeycomb. One honeycomb is like, what is it, 3 meters? Is it 9 feet? It's 9 feet, right? 9 feet is this, and this is 4.5 meters. So this is approximately the size of this components. And we tried to group it and to create some repetition. It was not possible because of the geometry. And I showed a movie we did in 2008 because we wanted to explain to the client why we just come up with a design, but why we need some time to develop a tool to make it happen. They became nervous in Shenzhen, and I had to send 6 engineers because they said, send more people. I sent 6 engineers to work on some other projects, but the guy who was programming this was a Stuttgart, so we kind of protected him from anything else. So this was, for us at least, in 2008, 2009, the first time we really used parametric tools to create a geometry, and we did it, you can imagine, we changed it a lot. I think it's 37 times we created a new set of data because of many aspects and an Italian architect. So you see that was more or less the interface. So we got the rhino shape and then we digitized it. So based on this shape we created all this honeycomb pattern. That's the result, so I think it kind of worked. And what as said, we just used the tool to create geometry data, and we handed that over to the Chinese contractors very early. But what I think was a missing chance, that we could have used it for much more. We could have used it to, let's say, really work on the performance of the scale. So, because at the same time when you create a geometry, you have all the components to evaluate the lightning, to evaluate energy gain, everything. You could put it in one model. So now it was in 2008. Now in 16, I think the tools are available. So you could plug in all this, let's say, disciplines, and get a powerful tool. And then you have the freedom actually to design an envelope in a totally new way. So I just want to illustrate that all these parameters could be fed into such a tool, and that was, that's the unread surface of the skin, and each cell, contains information about what this honeycomb needs to or has to do. So finally, I think that could change the way how we design, because this is the more traditional. This is the traditional way. This is, let's say, the way the Henry Ford or the way how we design, because we do it in linear. And then, there's obviously somebody sets the design intent. First, the second one tries to make it happen, and the last one has to do it finally. So I think there is a chance with these design tools, if we further work on that could be more iterative or integrated approach. So that you then could work in one solver space, let's say. And I think that's hopefully. I think it's up to you then to develop this and then to negotiate which parameter is important in which order. Thank you for your time.
Great. Thank you.
Okay.
John will be back and clean up. Saw some really interesting work, I think, from Ben. The sort of journey that DSR has gone through, and ending up at probably one of the most performative spaces out there in terms of how many configurations it can have, endless. And I think, Thorsten, your work is really interesting. I think, where you're coming from in fabrication and where these tools are merging. I think your last piece is so right there. I mean, I would say from 2008 to today, that's a space, that's not a long period of time, everybody. But in that period of time, the technologies have ramped up so quickly that we're now in this sort of integrated space. This is negotiating convergence right there. So we'll pick it up more, John.
Yeah, and again,
Thank you for this. And, you know, I think obviously the themes Ben and Thorsten brought up are certainly going to be repeated here. I'd like to say that we coordinated this together, but it's a perfect sort of transition point where Thorsten left off. We're only going to do 2 projects, one 2008, one now, and the focus, we're interested in terms that become super generic, BIM, VDC, building information modeling, VDC, virtual design construction. They don't mean anything abstractly. We're using digital models in an environment for coordination and the data associated with components, and being really specific about what we do with those. I mean, componentry and complexity in architecture and engineering and construction have been here from the beginning. We've spent thousands of years trying to figure out how to distill a complex form and environment down to its piece part component and communicate that to someone to build. That's the challenge. I think that's where sort of all are. And it sounds like we're all converging separately. We didn't discuss this, but we're all coming down to the same tools. They figured this out in aerospace and automotive decades ago. CATIA came out in '77. It was before AutoCAD existed, and it was 3D from the beginning. So these ideas, leveraging these tools, these technologies, it's here now. 2016, we have the computational power. How a building goes together, how anything goes together. Building models as a kid, you don't read anything. You look at diagrams. You look at the piece part A slips into slot A. And industrial design uses kits of parts, and automotive uses kits of parts, and aerospace is kits of parts. Of course, we believe that buildings can be kitted, parted, manufactured, and assembled on site. We are moving towards this as an industry, as an approach. And the plan, section, elevation, those 2-dimensional orthographic drawings are not the most sort of communicative way to describe a building or a product. To do this, which I think we've definitely seen Ben touched it really well, you have to be involved. This is collaborative. No one just does this and says, here, make my vision. You have to understand the material parameters. You have to work with fabricators. You have to work with experts, engineers. But that piece component, if you are involved in the ecosystem of how the thing is made, you can make a lot of decisions of what is made. And in certain cases, it can be self-jigging to the point where the instructions, you don't need any, because it can only fit together one way. So we, at any scale, at any sort of formal expression, we want to know every component in our building, but not just as sort of a discrete element. What are the connections? If we're going to say that this thing is made of 30 different types of panels, we need to know, are they really 30 different types of panels? But if you mirror it, that doesn't count. It's a different fabrication process. There's different components. Everything has a name. We don't know that this will be the name that the fabricator decides to use, but in the design process, if you think of it at this resolution, you're doing your due diligence. Someone eventually is going to come up with a nomenclature to the parts and components. So we don't pretend to exist outside of that. The Barclay Center was 2008, 2009, and we're in CATIA. V5, unique panels, 12,000, weathered steel, they're all different, blah, blah, blah. It's a unitized system. This is, it was fabricated, prefab, off-site. The weather enclosure, the secondary system, the ornamental steel, all of that's brought in one truck at a time and installed like Lego blocks. It's a product. To do that, every piece, again, this is CATIA, same stuff that people are using. It's a very high resolution geometric modeler. We modeled every part component with whatever information is needed to make it. So if it's a water jet file, it comes with a cut file. If it's a piece that's going to be cut by machine, it comes with the CNC code. If it's something that someone's going to cut and assemble by hand, we don't have KUKAs assembling these yet, then you have to make an assembly drawing or assembly diagram. But it moves out of the realm of drawing intent to bills of materials. These are quantity takeoff anymore. It's a schedule of parts and pieces, and it's a mindset shift that it shouldn't be restrictive to design, but it is something that this industry is going to start speaking, I think, more frequently. So these are the type of things. If you're going to cut this, what information does someone need to know to make these parts and components? So this is the kind of stuff you can, there were 950 mega panels. Each one has 50, 60 parts, and every part has subcomponents. So these drawings, there's a drawing for every one. We didn't make, we didn't go in and draft every one. These systems now allow you to put an incredible amount of information into a template. There's 950 different units, but there's only a handful of templates. So you put all that information in, and you can paste around the building. Everything comes with its information. All the drawings and cut files are created. They're automated. So no one makes these drawings, right? We don't need dimensions on any of the panels because they're all going to be water jet. Which is a negotiation. That's something you have. It's a relationship with a fabricator, with an installer, with a contractor. But all of this stuff, you need the information for the bend. That needs to be charted out from the machine. But everything else it needs to be tracked. So you start. If we're going to go direct to cut file, then what do people need to do to track this? If you start cutting, and all of a sudden there's 5,000 pieces lying around the shop, you need a way to track it. So you start becoming more involved in the process of componentry. So we can barcode things. We can start to, every piece that comes off the water needs a name. Again, this sort of nomenclature. It needs a way to track it. You can create, it's all sort of technology we have now. It's not rocket science. You can create iPhone interfaces. You can create apps to scan. Everyone's doing things in databases now. So if we're creating a part, we can provide a database of a list of them, and if you cut it and scan it, this will update. You can host a model online for you. You can navigate it. You can see exactly where something is in the fabrication process, in the install, even in the delivery of submissions, which we're starting to track now. But all this is real-time data. It's downstream. So that the V5, we're moving into the now. What we're doing in 2016, which everything. We need this environment. I think Thorsten's last slide of the sort of purple region of architect, engineer, contractor, all coming together. We need a platform. We need an environment to do it, and it is a three-dimensional environment. It's a database, and it is 3D. So in 2009, we had folders. We still do for the most part. But each one of so there's 950 mega panels. They all have their name. We have an organization structure so we can find everything. This is your due diligence. This is how you can find anything. You don't go insane if someone says this part didn't fit. Which part was it? It's in 3951. It's this piece component. So you navigate. We're in the systems are in the cloud now. The evolution of these tools. COURTYARD is now as a system, it's all cloud-based. So I can just type in a name and every piece component associated with it immediately becomes available. I can pull up any information from anywhere at any point. This is, in the client, in the rich client, this is in the software. I can click it, edit it, any view, anything you want is there. But online now, all of this stuff, HTML5, all these things, the model components, you don't need a super PC to do this. You can navigate parts. I can do this on my phone. You can explode the pieces parts. You can see in our tenant, which is our environment, this is our collaboration environment. You can see who's made what part, when, how many of them. All of this stuff is accessible in any sort of device. This is the project. And a lot of people access this. The fabricator, designers, hopefully owners soon, stakeholders, because this is where it will sort of drive. But the reality is once we start doing this in any medium, we're now working overseas. We can do the same process we did for Barclays now in a different continent with a fabricator, what we can do before we even start the project, we know the full scope, it's already in the right environment, we're not going to rebuild models, we're going to evolve. We start with the design surfaces, curves that all have their performative, shading criteria, all the things. But we can go in and say, look, we'll interview different fabricators, we'll give you a sample file. You don't have to make it this way, but here's one unit. There's 3,000 units on this project. Here's one, and here's a set of instructions. If you make this, you get a sense of what parts you may want to leave in, leave out, how you want to build it. And you can put a price to this. You can put an accurate cost, process, assessment of what it will take to make this building. We can do that at schematic design. This stuff becomes very important because it's real. It's how we're organizing the project. So the project is a three-dimensional environment. How we organize it from design. It's 3 bars. The bars are blocks. The blocks have building components. They've got structure, interior architecture, a facade screen. The facade screen has enclosure systems. It has window wall. It has rain screen components. All of these things is how you organize the project, and we can get immediately into the systems before we know how we're going to make it. We know that these are individual panels. We know they've got specific criteria in terms of widths, lengths. We know that they're going to have parts and components. We don't know what they are, but we can put placeholder products. This is going to be a product, and it's going to have pieces in it. So we can set that up from the design, from the beginning, and evolve the model as we get information from fabricators, as we have information from contractors, fabricators, on-site logistics, laser scans, which we'll get into. All of this stuff is happening in one environment. So this super boring project schedule, the timeline of a project, there's a task, design a connection to this, create a laser scan survey of this area. All of these tasks are things to do. If you're in the same environment, this can be viewed this way. It can also be viewed this way. This is the exact same project schedule. All of those are containers to do something. Design this connection, laser scan this area. All of that is a container for the model. If you design something, either sketch an idea, attach that sketch to the task. If you modeled it, attach the model. If you laser scan something, attach the point cloud data to those tasks. And what we're creating is this continuum, this one sort of environment that anyone, of course their permissions, but anyone can access and coordinate the information they need in a parallel process. So the model becomes a place to do drawings, sketches, any criteria is all stored in one environment. Now what that does, we're a very capable facade fabricator, but it's not the most sophisticated outfit. They've got ways of doing things. This is the schedule of the install, so, we'll start there, we're gonna go that way, and we're gonna go here, and then we'll go that way, and we'll go there and go that way. So we can take that, and it makes sense to us. You can quickly we have all the information, you just say, here's the schedule, assign it, each part is a task, you assign it. This is not animated, this is just playing off the schedule. We can reconfigure the schedule. What if we do 2 crews? We can start analyzing the impact of the project timeline sort of in real time. This is the engineering drawing we received. How long can a purlin span before it needs a support? And this is not to sort of insult the engineers there. We need information, and the fastest way to get it can go 2200 millimeters. That's all we need. We don't need a fancy shop drawing set. We don't need anything like that. We can plug that into our models. We're going to create shop drawings, and this is levels components. We will have bills of materials for everything. We don't need to review a shop drawing if we're seeing the fabrication components in place. So this is a process that sort of transposed itself very well from 2009 to 2016 in the cloud. This is Botswana right now. It's a little further along than this, the visual mock-up sort of going up. But again, this idea of we're delivering kits of parts. These things come in from Cape Town, they come from South Africa, manufactured as pieces in a box, wrapped. They come to Africa in the basement of the building, and there's a team of people that assemble these. It's 3,000 kits, 3,000 IKEA parts, Bjorns or whatever they are, and then you put them up, and that's it. So this is sort of a weird way to end, and I hope you don't get sick, but there's things like, the things that make this stuff work is we have the site, we have the existing conditions digitized. We have in our models, our fabrication models, we have the scenario. We know when something will fit and when it won't. And we scan in multiple iterations. Technology is moving that you have to believe it's inevitable that sites, conditions, Google, Tango is scanning in real time. The environments will be digitized in real time. So you will always have a survey of what's there. So what this starts to mean is we start playing with virtual reality, not for the sake of an immersive rendering, but one, we realized we didn't have any sense of the scale of digitally we're just floating around assembling these, it's easy. So we start taking these and exploding our components, and you've got to go into HTC Vive and start grabbing things and assembling it. So this is it's more refined now. This is our sort of alpha iteration of someone in the thing going and starting to put this together. It's a novel. It starts obviously as a very novel idea of what does it mean to put this together. Here's the assemblies, do this. But the novelty starts to become very real when it's a way to sort of pre-build, get a sense of the size, scale of these things. And when you're out there, to understand what this piece is that you'll be lifting. Again, apologies for that. But this is the method where we will be living in these environments to coordinate. That's sort of the I think inevitable reality of it. So it's a weird way to sort of end there, but that's that.
That's great.
Yeah.
Thank you. So we have some time for discussions and questions. So if I can have everybody up here. Great.
Hello.
Before I start, I have some questions, but I'd like to actually open up to you all. So if you have some questions to ask speakers, there's a lot of stuff that they've shown. So, anyone?
I have a maybe big question, and I'll try to make it specific. I would say, as a student, I'm not a student, but recently a student, getting into the world where you're working through your design projects into issues of rationalization, like getting more rigorous and specific about the parameters. I think we're always sort of in a conflict where we're between off-the-shelf products that do something for us, that either tile or tessellate something in a certain way, or figure out a panelization of something in a really simple form, and then techniques like optimizing a system with unique components into 12 discrete sets or something that are just, at this point in our education, is way above us. Just because there's no really off-the-shelf component for that in the software we use. I wonder what you see as the future of that sort of workflow for students. Like, where is the space now in design education for people to get into those more deep concepts of rationalization, parameterization?
I'll start.
John, by the way, teaches here. If you want to take his course, my first answer would be take his course in the spring, and you probably learned some of that. But
we definitely do. That course does deal a lot with if you want to parse things down to 30 unique types, that sort of slider of unique typology, and see what it does to the form. As a student, I think it's important to understand that this stuff is happening. I think, through the presentations you've seen, we can build any form, we can build any any shape out of any material. I mean, I think geometry rationalization is not the challenge so much anymore. So while you can spend time, you can learn how to do those optimizations, I think what, and didn't touch into the next step of what we're showing, which is what will be important. So it seems like we're reducing unfortunately right now, architecture is a lot of, the initial sketch. You spend maybe 10 to 15% on what it is, and then you spend the other 85 to 90% of the time documenting to people how to do it. And what we're talking about here, a lot of this is compressing, the tools that we have available to us. We can compress the time of the sort of how it's done so that we can spend more time on the why and what it is and its performance and all of the criteria that should matter, does matter, but we should spend more time on that. So it's not to say that we can now automate building production so we can do 100 times more buildings. We can now start being really, really smart. We can analyze, as we make a design move, we can have engineering feedback, we can have structural performance, we can have environmental feedback, but we can have experiential feedback. What is this space? Like, it performs super well, it's temperate, it's horrible. So why would we want to make that space? All of this stuff can happen at the same time. So it's important that you understand how the technology is evolving. We're moving towards manufacturing buildings, but I wouldn't necessarily go tunnel vision and say I'm going to figure out how to create fabrication models, because you have to assume that the industry's moving that way.
I guess I mean, from the DSR perspective, I think the model that you've showed kind of shows the future in a way of making buildings. I think we often, in our shop, treat each building as a one-off that's built from the ground up. Like, what we're going after is different, the envelope is different, the materials are different, the expression is different. Usually the problem that we're exploring is different. And I think that when you're asking about what the constraints are, I think that probably the tools that you have at your fingertips outstrip the ability of people in the field to actually assemble those things right now. And ultimately, in order to achieve really difficult things, you need to, in each project, discover what the constraints are. And the constraints aren't how many like pieces you can have or how many you can't have, or even what can the machine make, but it's like, what can the guy get on the back of his truck and take to the site and carry up with a couple of other guys, but not too many guys because it costs too much to put on the building. And so there's a primitive side to things that really does set the constraints of each project. And in order to truly understand how to use the tools effectively, you have to have that collaborative relationship where you sort of have some amount of time walking in the shoes of the contractors and the trades who are ultimately going to have to install the work. I think you demonstrated that really well. But I think that my feeling is always that the tools that we have at any given time are beyond what the industry is prepared to actually make, use to make things in the field. And I think that to actually push things forward, you have to be out in practice and you have to have that kind of collaborative experience working with contractors to figure out what is possible and how to push them and how to not push them too far so that you create things that fall apart or don't work.
I'm curious your input into that. I mean, you're talking about this interface, this issue between what might be possible in design and what is possible in fabrication, and yet, gosh, we've seen some things today that are just unbelievable in terms of their fabrication quality. I mean, frankly, world leading. You're right at that junction.
I think it's interesting. I saw the movie like this virtual reality, but you have to imagine there's gravity also. Like the bar you live there has some weight.
Yep.
But that's
easy.
I don't realize that. It's important to do that. But when I was say in the office, and sometimes you think it's kids on computers, so you have to be aware that what you do there, what you simulate there, it has to be. You want to build it. Otherwise, it's fun. it's a game. So I think that's important. I don't want to be the guy, the typical engineer saying that's not possible, but you have to think about that. And I think coming from university and starting somewhere, you probably have to be just curious, and you're skilled, you know a lot of things, but there's a lot of things coming back. And as I showed with my early projects, you learn a lot, and you get maybe some more. Even there's more. It enables you to do more interesting things. But you have to be open, and you have to be aware that what you can model in the computer is not necessarily realistic, but you should do it. I think, and it's important to do that. But I think what I think we use the digital tools more at the moment in the building industry as a clash detector. We don't really use it as a design tool. That's what I'm trying to say. I think we could use it, your BIM, and the US is much far ahead of Germany in using BIM and Revit. We discussed it 5 years ago, Craig, you remember that? I visited you and you said we are now working with Revit, and I had to look what it is. I mean, this is a very important tool, building information modeling, or what you do, really advanced. And I think also we have for designing something, we talk about convergence. I think that would be interesting to figure out what it could be. You can plug in a lot of tools in Rhino, which I think is a very interesting thing, because everybody can work with Rhino. Every student and young architect, engineer, they can work with Rhino. I think, and there's a lot of tools to plug in. Maybe this is toys too, but it could also give an idea of how you could create a platform where you can work together, because you have the same language. Right. I think that for me it's interesting to see what happens in 10 years when you are there and you're used to that tools. You cannot simulate to be an engineer, or environmental engineer, but you have the same language. I think communication is about speaking the same language. I think that's, for me, the interesting aspect also of that in the future.
I would follow on to that. You talked about these sort of environments to a certain extent, design environments, whether it was your piece on the Lincoln Center or what you showed, and your idea also, Thorsten, of this sort of general environment. I think the question for you as students, as practitioners coming forward, is that environment is there. There will be a product, a software, and it will continue to get more rich. You have some decisions to be making in that space. To a certain extent, the use of technology today is more limited by what we need to do rather than what we can do. And I would take a little bit of issue with, I think you're saying that you can do more with technology than you can fabricate. I'm not quite sure about that. I think you can do virtually anything today. I think we are in a golden age of technology. The question is, what are we doing with it? Your challenge is to take all of these amazing technologies and create something with it, but thinking about what you're putting into it. When I was, honestly, when I was first becoming an engineer, it was a lot easier. The demands were simpler. The idea of what we were trying to do was frankly, really lightweight structure from A to B, and okay. I mean, today, there's so many other things to be thinking about within the demands and the performance of that space. And I'm kind of curious of your individual experiences. Maybe you could describe to the students a project that you felt those sort of crisscrossing demands or frustration. I mean, because it's harder. It's a lot harder to design for multiple performance requirements than just a single performance requirement.
I mean, I could say one thing about the shed in particular, which is because so much is possible now. I mean, there's a lot of hand involved in the fabrication, but all of the steel parts were, laser cut effectively and then pieced together and then welded and ground and all that kind of stuff. And the glass is fabricated by the highest end glass fabricators in the world, and et cetera, et cetera. There probably is a limit to how many of those things you can layer on top of one another and the thing continue to perform well. I think we're hitting a threshold condition of too many layers of complexity saturation, and I think that may be the experiment of that project is how far can you actually go. and it still performs at the push of a button, and it's operable and maintainable over time.
So
That's
it's
the
the
kinetic
opposite.
structure. The glass doesn't bind, and it doesn't fracture, and the shades don't bind, and all that kind of stuff. And even with the planning in of all that for failure and repair and all of that, it still is we sort of call it a cantilever off a cantilever off a cantilever off a cantilever, and at a certain point you put one too many cantilevers on the end of it, and you learn that you've gone too far. So maybe that for us is just the lesson is when have you taken on too much complexity and tried to have one thing do too many things. That's maybe a little self-reflective. Hopefully we'll keep that in the room. It opens up, but because so much is possible, we go so far, and you wonder how far is the right amount.
But it won't stay in the room for sure.
Yeah.
No, what I think is interesting, the shop and Diller, Scofidio, Renfro. What I like with what you do is that you're influenced from the process. The result is influenced from the process, and that's ideal for us, all of us, for engineers, because there's a collaboration going on. And as you say, maybe you avoid the last cantilever, the one where it's coming down again. But on the way there, there's many opportunities you can explore, and that's different. You have shown the first pictures of this basilica or cathedrals. This was set before, and it was done like this. So, but now project starts, and you explore ways, and it's the result will be probably a bit different, or it will generate, or different ideas. And I think it's interesting that you are open to that, and I appreciate it. I think that's, if you talk about multidisciplinary or a lot of performance parameters, then you have to be open, to developments, which a lot of influences come from any other discipline, and design disciplines, but also fabrication and so on. And sometimes you get more than you thought you could get. That's what I showed with the hydroforming or biodegradable composites whatsoever. So I think I think you have to be open, I think much. And as you said, we started in the 90s, and that was one parameter optimization. Yeah.
Math.
Yeah. Yes. Right.
It was weight.
And now it's much more.
It might be, in 10 years' time, it might be behavior. I mean, who cares about how heavy or how complicated the glass is? It might be about the responsiveness of that structure vis-a-vis how hot or cold you specifically want to be, depending on how you're interacting. I mean, we should, layering on. I mean, as much as you say the cantilever on the cantilever on the cantilever, I think we're going to continue to go. A couple of them will break, and we'll learn, and hopefully it won't be ours. And then
We couldn't negotiate gravity.
Question. So if we're talking about costs, the thing is, prefab architecture is always about making it more rational and making costs lower. And anyway, we're seeing this transition between old prefab and new prefab, because some of the things you showed are made out of the site and brought to the site, etc. But are we still talking about processes that are cost effective, or are we at the point where this kind of technology is experimental and not cost effective, but we'll get to a place where it once again relates prefab and cost effectiveness? I don't know if I...
Yeah, I mean, I definitely think that these cost effective is a driver for a lot of these, and whether it's because it's prefab or even the newer versions of prefab doesn't mean that it requires some sort of technological process that is more expensive. Often it's ways to sort of automate traditional processes, and even if it means automating the process to create fabrication tickets for someone to do things in a very standard method. I don't think all of the stuff will be driven by cost. That's the inevitable part of it. We have the tools now to automate, to reduce the waste of production, to incorporate an incredible amount of information. So, to Craig's point, if we start incorporating sun shading into the structural system, maybe they get deeper, maybe you need less parts. that's not a fabrication issue now at this point, where you're now analyzing both the environmental impact and the structural performance. So that's happening at the same time. If we start doing acoustic analysis of what it does to the space, all of these things can be analyzed at the same time, to the point where other industries even have, they have people where to lift that component now, creating this incredible solar shading mechanism that provides amazing acoustics, now puts it past the point where two people try to lift it and the little simulated elbows or shoulders turn red because that's too much for two people to lift, which will then require a different type of instrument to lift it. All of that, like other industries have these tools. It's not sci-fi. It can all be analyzed at the same time. It's all moving towards creating a product at as fast as possible in the most efficient cost. So these processes are more expensive. It's almost going to be baseline, and you'll have to be lean and economical about how you design things.
I mean, I would add to it that in our cases, there was a cost component to a couple of them, but often it's, you simply can't, you need to prefabricate. For example, in the Tully Hall example, we had 16 months to do all the work from demo to opening the space up again. And there was both a quality control and fabrication side that was there was a much higher degree of quality control in the shop, but also in terms of the schedule, you could assemble all the parts, pre-fit them together, make sure they all fit, put them in crates in as complete a form as possible, and bring them in and install them in the fastest possible time. And so time was the constraint. In the shed, it's the same thing. It's quality control of the shop environment when you're fabricating the parts, and then it's also, you wouldn't want to be on site fabricating something like that. There's not the available laydown area, and you wouldn't want to fabricate something and figure out it was wrong on site and then be stuck having to fix it on site. And so there's a lot of really good reasons to go the prefabricated route. Sometimes it can be more expensive, strangely. He would probably say not, but it's not always necessarily cheaper in terms of money. Sometimes it's cheaper in terms of time, or it's great benefits in terms of quality control of the environment.
But I think I try to compare car industry with the building industry is difficult because the car is, because each building is a unique thing, it's a prototype. You build a prototype every time. And the car is, everything happens in a controlled condition. But building means you go somewhere, it's an uncontrolled condition. And you have to imagine like a welding in a workshop compared to welding on site is factor 3. So they have to, let's say, estimate it's 3 times more expensive to do something on site, to control it, than you do it in a workshop. So for sure, we all think you have to prefabricate as much as you can because you have to avoid the risk on site under uncontrolled conditions. So I think that's for sure, it's important. So I think, and you say maybe it's not, every time it's not cheaper, but you take risk away from something which you can control.
As a student, I was a practitioner for many years, and now become back to a student. It was really life-changing experience for me. In the past, people say AutoCAD will transform the new industry to differently, and then now it's the BIM that you will change the architecture scene completely differently. How do you guys see because I see your both shop and DSL, the practice are very non-traditional than majority of the office out there in the world. So how do you see the approach that you guys have will inspire the architectural world, or would that be to inspire change the scene of the?
I mean, I'll offer the first one because you'll get a better answer from the others. But I think we're very promiscuous with tools. Like, we don't care. We have no loyalty to tools. I think I draw with a pencil most of the time, and I honestly couldn't open and use a Revit file myself. I work with teams of people who have that skill set and are able to do it. We have people on staff who do CATIA, Rhino, Grasshopper, Max, from visualization through all the different stages of design, through fabrication, communication. But as soon as the tools change, we go to the next tool. Like, I don't think we care about what tool it is as long as it's the best tool for the job. So I don't know if that really answers your question. I think there's industry-wide standards. Everybody uses Revit on every project now, but I think that at the end of the day, to do truly inventive work, you have to go to where the right tools are. And I think you guys have a much more refined perspective on that because you're much more engaged, in fact, in the construction end of things. But I think at least that's our perspective, that you should be very versatile and be willing to move very quickly from one tool to the next.
100% agree. I definitely consider ourselves agnostic in terms of the CAD. CAD is CAD. Whether you get something from the manufacturers using SolidWorks to create a part that you're going to assemble in a COURTYARD file that you then export in and assemble it into a Rhino file, we use everything. And I do believe there are people that will argue, but I believe you can be as precise in Rhino, 3D Max. You could use SketchUp for fabrication if you wanted to. I mean, there's a digital craftsmanship that is involved in this, and it doesn't matter if you learn one CAD. Other CAD does the same stuff. The buttons are different, but it's about being very deliberate and intentional of what this model is used for. A surface in Rhino can mean a lot, as long as people that are all operating on that surface respect what that datum means. This surface means the outside face of glass. That means that the glass is this thick, which means that there's a spacer that's this thick, that there's then a system that goes this deep because it needs a mullion this deep to hold it, and there's a clip that then sticks out the opposite direction from that surface. A surface can mean a lot, but everyone involved needs to understand and sort of have a respect and craftsmanship in the digital environment. It's not about a tool, it's a mentality. And to that I will say 3D is, the 3D environment is incredibly valuable. And we draw a lot too, but the 3 dimensions, having a piece and then also clicking that piece and then the data associated with it, but that's a whole other thing.
Well, I think I just want to add one thing as a German engineer.
German.
Yeah.
We get your German.
Whatever it means. But I think, compared to, let's say, Europe or Germany, the architects don't use that much these digital tools, and I think I really appreciate and I really see how that's developing here. So I said, just being back from Germany, I was in Germany last week, and we had this discussion also about a lot of different tools they use, but there's no, how shall I say, they don't really use it to design. And even the younger colleagues use it, but it's not in their mind that they could work with it actually. So that's interesting. That I think, especially the two of us you represent here, really actively work with these tools and make it as a part of their architecture.
I find that really interesting, to be honest. It's almost hard to believe, but it's a really interesting perspective.
But going back to even your Frank Gehry example, where the way that they worked at Gary's office was to make a physical model and then literally draw it into the 3D environment in order to describe it, because they didn't know how to do it in the beginning any better way. I think it's that resourcefulness that kind of is exemplary of like being agnostic about tools. Like you just figure out what tool you need to do whatever it is you want to do.
And in that sense, just to piggyback, agnostic about the role too. There again, it's sort of respecting the environment. In the future, 10 years, are architects making fab tickets? Probably not. There's no reason to. If fabricators, contractors, even owners become sophisticated enough to use these tools, someone's going to make the fabrication model. It will be a model. It will be, because we need it for simulation, for advanced, to do all the criteria that, in parallel, all of that analysis, the models are key. But architects won't necessarily make it. And even a contractor, depends. It's all happening in one environment. So,
I would comment on the role of the tool. You just said the role of the tool, and that's really important. We have to also see this emergence from representational tools. This environment that we might be coordinating things in, or drawing things in, or even doing fabrication tickets in, to something that is actually more computational. And I actually think we're in that sort of phase now. Open source tools getting plugged in, that are more computational in nature. And those computational tools start to help us negotiate this zone. They start to help us make, of all the complexity, they start to help us compute, not just represent. I would say reflect on some of the things that you're learning at school. Simulation in particular is, I think, a really interesting area because it's beyond BIM, it's beyond CAD, it's beyond representation now. You know, the sophistication of BIM as in the aerospace industry, maybe from the 70s, from the 80s, we're looking now only at CFD modeling, computational fluid dynamic modeling. You know, and as these tools, you're going to see more of this in your careers as these tools emerge. And it's another layer of complexity, and yet it's a way of sorting out that complexity and helping you solve some of those problems. I think we're just about out because I think everybody is off to their midterm. So I wanted to say thank you to all of the speakers, John, Ben, Thorsten. You guys are amazing. Appreciate what you are showing. This is right out at the bleeding edge. And I really thank you very much coming up to GSAPP, coming up to Columbia, showing your wares. Please come back soon. Come back for crits. Come back for some lectures. Love to have you more part of the school. Thank you.